3.4. So in 3.3, we talked about the first derivative test. We talked about increasing and decreasing functions, right? Maxes and mins, all those good things. In 3.4, we're going to take it one step further. Instead of talking about how the graph is going up and down, right? It's increasing or decreasing. We're going to talk about the shape of how it's increasing or decreasing. And that's actually called concavity. And concavity can be done in two different ways. You can do concavity using the first derivative test, and I'll show you how. You can also do concavity using a second derivative test, which is going to be introduced in this section. So there's a secondary test that we can use. Let's talk about concavity. You have seen this before. In particular, the first time you probably encountered it was in an Algebra 2 course where you talked about parabolas. Did you have something that was opening upward or was it opening downward, right? And sometimes you'll hear language, does it hold water or does it dump water? It's another common language that people will use. But what it actually means to be concave up versus concave down from a calculus perspective, it works. I mean, it's still the same thing, but it's a little different perspective. So for a function that's differentiable on the interval I, the graph of f is concave up if the derivative is increasing. It's concave down if the derivative is decreasing. So when we worked in section 3.3, we didn't talk about the derivative increasing or decreasing. We talked about where the derivative was positive and negative, right? And the derivative being positive and negative told us something about how the original graph was increasing and decreasing. So if we're wanting to know where the derivative is increasing and decreasing, we do that by finding its derivative. And the derivative of the derivative is known as the second derivative. So this is a test for concavity. It's not the first derivative test, it's not the second derivative test, but it feels very much like the first derivative test because we're taking a derivative, setting things equal to 0 and solving with a number line, okay, with test points. So suppose that the derivative exists on an interval. I'm actually not sure if what I just said was true. This is the second derivative test is later. Okay, I didn't think it was titled that way. So suppose that the second derivative exists on the interval. If the second derivative is positive, then the original graph is concave up. And if the second derivative is negative, then the original graph is concave down. So I'm going to go back to the screen before to make the connection. So this is saying that it's concave up when the first derivative is increasing. But the way we find if something is increasing and decreasing is that we take its derivative, and if the derivative of it is increasing or is positive, it's increasing. And we go through this and we say, okay, it's concave down. The derivative is decreasing, and that's when the derivative of the derivative, the second derivative, is negative. So the process by which we do this feels very much like the first derivative test, because it really is. It's an application of the first derivative test to a new function, which is the derivative that we were just working with. All right, so let's take a look at some examples, because the process is very similar. The directions say to determine the intervals where the graph is concave up and concave down. So anytime something says concave, when you see that word in a question, that's like what a trigger word, right? It should tell you concave. I'm talking about second derivatives, kind of like back in middle school when they were working with keywords like sum. When you see the word sum, it means add. You don't even have to think about it anymore. Every time you see the word sum, you know it means add, right? You see the word product, it means multiply. Okay, this is the same thing. This is one of those keyword things. We see the word concave, we know second derivative. So this function in particular is a very nice function because it's a polynomial. So I'd like for you to take the derivative, and then once you have that, I'd like for you to take the derivative again, and then we'll check to make sure everybody has the same things. Take, 20 seconds or so to do this one. All right, what do you get for the first derivative?
4x cubed minus 12x plus 2.
Okay, nod your head if you got that. Okay, good. So somebody else, Jeffrey did that one, so somebody else give me the second derivative, the derivative that you just got of that derivative. Okay, go ahead, Bree.
12x to the second power minus 12.
Fabulous. Did everybody get that? Nod your head if you got that part too. Wonderful. So basically, we're just doing one more step, doing another derivative, and then everything else is going to look the same. We're going to set it equal to 0. We're going to solve. We're going to draw a number line. Sound good? Check test points, positives and negatives. All right, so we're going to set this equal to 0. So I have 12x squared equals 12. So what does x squared equal? Well, not yet. Okay, so there will be a plus or minus, but not yet. I left mine as x squared. So it'll be x squared equals 1. So you're jumping ahead of me already. So x is equal to positive or negative 1. Yeah, good job. Okay, so I actually have 2 test points coming out of this, which kind of makes sense because the second derivative was in fact quadratic, right? Yeah, so two values where it's equal to 0 is certainly reasonable. Number line then. On my number line though, oops, that's a little high, I have 2 locations to mark, -1 and 1. So I need 3 test points. Okay, somebody give me some test points that I might want to test.
0.
0 is a lovely one. I like that one. What else? -2. Okie dokie. And 2. All right, and again, there's nothing special about those. You can pick anything you'd like within those intervals. Where will we plug those test points in? The second derivative. I'm going to box mine in. We're going to plug them into this. Right? We're always plugging them back into the derivative we just found. So if I put in the -2, what will I get? Okay, is positive or negative? Positive. And then what happens when I plug in 0? I get a negative, and when I plug in 2, a positive. Okay, is everybody good so far? What I don't want to do, that I have been doing, is draw these sort of increasing and decreasing lines. That's not helpful. Because that's not the information that this graph or this number line or this sign chart, whatever you want to call it, is actually conveying. It's conveying information about concavity. So Jared's back here drawing like arches in the air, and he's exactly right. There's an arching effect going on. So on the first one, and in fact I'm going to shift my graph down so I can draw a little bit above it. The fact that it's positive means that it's like this. It's sort of a U shape. And the same thing over here for the positive. And the fact that it's negative would be like the parabola opening downward shape like this. Okay? So if you can imagine connecting these, because these are not, of course, connected, I've just drawn them above each of their components, you almost have like a W-ish shape going on maybe, right? Which we'll confirm in a moment. But right now, our graph, or our question simply asked us to determine where it's concave up and concave down. So let's do that. So the positives are the concave ups. So where is it concave up? Negative infinity to -1 and 1 to infinity. You guys are getting this really well. And then concave down? What do you got, Nick?
Nothing. You made a Buzz Lightyear joke.
Okay. To infinity and beyond, of course, absolutely. And then -1 to 1, right? Are we good? Okay. Just for fun, let's graph it real quick so that you can see that it actually makes sense. I know that's not part of the direction specifically, but I think it's always good to confirm and have ways to confirm that you're looking at things the right way. So we graph this with the original function, and the question is, does it do this? Does it in fact go up and then down and then back up in some fashion of this sort of convoluted W? Looks like the pre-K kid learning to write the W, right? Lots of loopies. Yeah. Is that how you write your W's? Oh, no. Okay. That's encouraging, at least, to hear that's not how you write your W's. Okay, does it have this general shape, for those of you who've put it in? Awesome. Okay, so let's take a look at the next piece then. Now, when in fact it changes between increasing and decreasing, we had maxes and mins, right? Those were the things we're looking at, decreasing and increasing. And when it changes between concave up and concave down, we have another point of interest. In particular, it's called an inflection point. So suppose that the function's continuous and the graph changes concavity, either up to down or down to up. I don't care, like the concave up to concave down or concave down to concave up. Then the location where it's changing concavity is called an inflection point. So if we were to go back to this function that we just did, we would have inflection points. I don't know what the y coordinates are, but they would be occurring at 1 something and at -1 something, right? There are 2 inflection points here because the concavity changed twice. So you can have multiple inflection points. You can have 1 inflection point. You can have no inflection points. Parabolas have no inflection points. Parabolas are constantly concave up or constantly concave down. So when you do have them, they're called inflection points. So how do you find inflection points? Well, how did I find the -1 and the 1 over here? Where'd those numbers come from? Somebody say it so we can move on. Y'all know it. You're just like staring at me today. What happened? The second derivative set equal to 0, right? Yeah. So that's exactly what this theorem says. The point of inflection will occur when the second derivative equals 0 or does not exist. We just didn't have that happen in our function, but it's certainly still a possibility. Okay. I don't have the ability within this presentation to pull up my last presentation that I just did, this last slideshow, but do you remember that funky one that we had that looked like this? Y'all remember that? It didn't have a max or a min, but this location right here actually was an inflection point. Can you see how this piece right here is concave up and this key piece is concave down? It is. This is an example of an inflection point where the derivative's second, or the derivative's derivative, the second derivative doesn't exist. The derivative didn't exist, so the second derivative is certainly not going to exist, right? But this is one of those. So just because it doesn't have sort of the interesting maxes and mins doesn't necessarily mean it doesn't have other points of interest like an inflection point. All right, so we're going to find the inflection point of problem number 2, and this is the last problem we'll do today. Okay, problem number 2. Find the points of inflection and to discuss the concavity. But this one is a bit more interesting than the last one, just because there's a little bit, well, because the powers are higher. That's really why, right? There's a little bit more going on. So you have a couple of options. If you think back to the exam that you just did that had powers that were higher and you had to multiply things out. So let me tell you your 2 options and we can decide what you guys want to do in terms of me doing it on the screen. If you want, you can multiply everything out at the beginning. Okay? If you do that, you're going to have to multiply something by itself 3 times. That's one option. Second option is that we can take the derivative, which will include a product rule, and then we can multiply it out. At some point, we're multiplying stuff out. I mean, have no doubt about this. It's going to happen. And that's partly why I use that test question that I do, is because you got to be able to multiply these out. Otherwise, we're not going to be able to find the rest of the pieces of information. So what do you guys want to do? Do you want to multiply it out at the beginning, or do you want to take product rule at the beginning? You want to do it at the beginning? Okay, cool. So if we do this at the beginning, I'm going to do the x last. I've got x minus 4 times x minus 4 times x minus 4. And no, that's not x cubed minus 64. It doesn't work like that. There's no distribution, unfortunately. I wish there were. I really do. It would be so nice. So much more friendly. Okay, if I multiply 2 of these together, I've got x squared. This is minus 4x and another minus 4x, so that's minus 8x plus 16. I'm going to save the times x for last. And then if I distribute the x through each of these, I'm going to get x cubed minus 8x squared plus 16x. And then I'm going to distribute the negative 4 through this. So I have negative 4x squared, positive 32x, and negative 64. That was all done in real time. You know, like Facebook Live kind of stuff, which means that errors might have occurred. Did you see any errors? Did I do it okay? It's all right? Okay, good. We need to combine some like terms, and we need to distribute the last x through. Let's combine terms first. There's an x cubed. I have negative 12x squared. And then I have, good grief, positive 16, negative 32. Is that right? Okay, 48x. And then the last piece was minus 64. And if I go through with my x, I have x to the 4th minus 12x cubed plus 48x squared minus 64x. I'm so sorry. But we're ready to do the easy stuff now that we did the hard. What's the derivative of this?
4x cubed.
Mm-hmm.
36x squared plus, is that 96x
Mm-hmm.
minus 64.
Wonderful. All right, second derivative. 12x squared minus 72x plus 96. Moment of truth. Let's check my notes. Oh, I didn't do it this way in my notes. Of course, I did the product rule. We're just up a creek now. What would be our next step? We've got the second derivative. Yay. Now what? Set it equal to 0. And these are really big numbers, but definitely we think, I mean, they're all even, so they definitely all divide by 2. Is there anything else that they all divide by?
It's 96 and 98.
Oh, thank you. That will help. I'm sure it will, because it's right. Okay. Do they all divide by 12? I hope so. Okay, so x squared. What's 72 divided by 12? 6. Oh, I like that number. And then how about 96 divided by 12? 8. So this is where those multiplication facts of 12s would come in really handy that I never learned when I was y'all's age. They learn that now. I don't know if you did or not, but my 5th graders in the hallway did. Okay. We want to factor, and all these numbers are so much better than the last numbers we just had. How will this factor? -4 and -2. Okay, so what are the x values that I actually get out of this thing? 2 and 4. Okay. Okay, so x is 4, x is 2. And we're doing a number line, right? 2 and 4. Okay, I'm going to pause right here because I want to actually finish this without having to feel like that I'm talking 90 miles an hour. We're going to plug in the interval numbers, right? We're going to get test points, plug numbers in to the second derivative. That's going to give us information about concavity, and once we have that information, we'll be able to find those inflection points. And we will finish that next time.